Hey you guys, this is Mr. Millings, and today we're going to talk a little bit about how atoms release energy in the form of light, and then we're going to take a look at some emission spectrums. Okay, so when you go to that 4th of July fireworks show and you see all of those pretty colors, what is happening there? Well, that's what we're going to talk about right now. We are going to talk about how atoms emit energy in the form of light. So let's suppose we have a little lithium atom, and this lithium atom consists of 3 electrons. It has one little valence electron here, and if we take a look at this lithium atom right here, it is currently in the ground state. Okay, a ground state lithium atom, what that means is that all of the electrons are occupying their lowest possible energy levels. Okay, so all atoms want to be in a ground state, and this lithium atom right now is in a ground state. But if we pass electricity through this little lithium atom, or if we heat this lithium atom up, it's going to enter an excited state. Okay, so we have a ground state lithium atom right here, and we have an excited state lithium atom right here. And if we pay very close attention, what we'll notice is that the valence electron in the excited state lithium atom here has jumped to a higher energy level. It has jumped to the 3rd energy level, if you want to consider it that way. So this little valence electron has jumped to an outer energy level, and that is exactly what happens when atoms get excited. When atoms get excited, what ends up happening is their electrons start to jump up to higher energy levels. Okay, so we have an excited lithium atom here, and here's the thing about excited atoms: they want to be in a ground state. Okay, they feel much more comfortable with being in a ground state and having an electron configuration that looks like this right here. So what ends up happening is that this electron that is now in an outer energy level, or a higher energy level, is going to jump back down. It's going to jump back down into this energy level right here, and what ends up happening when it does that is that it's going to have to release a certain amount of energy. It's going to have to release energy in order to go from an excited state back down to a ground state. And this energy that it releases comes in the form of light, a form of electromagnetic radiation. Okay, so as this excited lithium atom goes back down to a ground state, what ends up happening is this electron here moves back down to a lower energy level, and it's going to release a photon of red light. Okay, so little photons are released. Okay, remember that photons are a form of electromagnetic energy or radiation, and this little photon here has a certain amount of energy, and if we wanted to measure that, we can quite simply do that. In an earlier video we learned that to figure out how much energy this little photon has, we're going to take Planck's constant, multiply it by the frequency, and we'll find that this little red photon of light has low energy associated with it. Okay, so that's what's happening there. That's what's happening when we see the fireworks show on the 4th of July. What we're seeing are a bunch of different types of atoms that are entering into an excited state due to the different little explosions that you might see. And then those little electrons are going to jump up into higher energy levels, and they don't want to be in this excited state. They would rather be in a ground state. So these little electrons are then going to jump back down into lower energy levels, and the way they do that, they're going to have to release energy or different photons of light. And so what you see at the fireworks shows, you'll see your greens typically being copper, and the green light is associated with high energy photons that are being emitted by those copper atoms. And you have strontium and lithium being red, which are associated with low energy photons of light. Alright, so that's how atoms emit light, and that's how atoms tie into the electromagnetic spectrum and the visible light spectrum and electromagnetic radiation and waves. Okay, so now let's take a look at the flame test and see what's going on with that. Okay, so knowing that atoms can emit light or energy in the form of energy in the form of light, and knowing that that energy can come in different different amounts of energy, right? High energy or low energy. What we can do, or what scientists or chemists can do, and you've probably seen this in your chemistry class, is we can do a flame test. Okay, a flame test is an analytical procedure used in chemistry to detect the presence of certain elements, primarily metal ions. And so what ends up happening is you have a Bunsen burner right here, and there's nothing placed in this Bunsen burner. This is just a flame. But when you start placing these different metal ions or metallic compounds containing arsenic or calcium or copper or potassium or sodium or strontium or other metallic ions, what you'll end up seeing is that they emit different colors of light, which correspond to different amounts of energy. For example, when we take arsenic or arsenic compounds and we put it in this flame, it's going to emit this little blue flame right here. And blue wavelengths or frequencies of light are associated with higher energies, right? Whereas if we put calcium or a calcium compound into this flame, it's going to be brick red. So these calcium atoms are releasing energy in the form of light, and this light happens to be red, and red is a low energy photon of light. Okay, if we take a look at copper, copper is typically green, which is associated with a high energy photon of light being released. If we take a look at potassium, we have lilac. If we take a look at sodium, like sodium lamps that maybe you see in the Walmart parking lot at night, those are going to release yellow photons of light, which are kind of medium range energy or medium energy photons that are being emitted from this sodium atoms right here. And last but not least, we have strontium right here. Alright, so the flame test just shows us the different amounts of energy or the different photons that are released from the different atoms, and those photons correspond to a different amount of energy. Alright, so what we can do now is we can actually take a look at atoms' emission spectrums. And an emission spectrum is basically an atom's fingerprint. Alright, for example, if we take a look at hydrogen, here is the emission spectrum for hydrogen. Alright, so when we excite hydrogen, what ends up happening is that the electron in hydrogen is going to jump up to a higher energy level, and then when it goes from an excited state back down to a ground state, it's going to start to release energy in the form of light. And we can see here that some of that energy is going to come in the form of red photons of light. Some of that energy is going to come in the form of this light blue photon of light, and we have some appears to be indigo photons of light, and we have this blue, dark blue photon of light as well. Okay, so you might be saying to yourself, well, how come we don't only see one little line, since hydrogen only has one little electron? Well, that's a good question. And so when we take a look at this hydrogen, we are talking about the elemental hydrogen. It's not just one little atom. It's comprised of billions, if not trillions, of hydrogen atoms, and some of those are releasing red photons of light. Some of them are releasing this light blue photon of light, this dark blue photon of light, and this indigo or violet photon of light that we see right here, which are all corresponding to different amounts of energy. Okay, so this is the fingerprint of hydrogen, right? This is the emission spectrum of hydrogen. If we take a look at helium, this is a little bit different. We have yellow photons of light that are being emitted, and we have other little photons of light that are being emitted over here. Alright, so this is the fingerprint or emission spectrum for helium. And if we take a look at boron right here, here's another emission spectrum. For boron, we have red photons of light being released by boron atoms. We have orange photons of light being released by boron atoms, etc., etc. Okay, so this is like a fingerprint. And we use emission spectrums to determine the types of atoms that are in distant stars, light years, many, many light years away. Okay, we collect that light in a telescope, and we're able to determine what elements make up distant stars that are hundreds of millions of light years away based on the emission spectrums, based on the atom's little fingerprint here. Okay, so understand how emission spectrums work for the different atoms. Alright, so if you take a few moments to just pause this video, and we can take a look at, or you can take a look at the emission spectrum of alkali metals and alkaline earth metals. So here are the alkali metals right here, lithium all the way down to cesium. And here are the alkaline earth metals over here, from beryllium all the way down to barium. And what we can see if you pause this video, you can take a look at all the emission spectrums for the different elements here. For example, here's lithium, right? We have we have green photons of light being emitted. We have red photons. We have orange photons of light being emitted. If we take a look at sodium, right, all these different little photons of light are being emitted from elemental sodium. All these little photons of light are being emitted in elemental potassium as those atoms go from being in an excited state down to a ground state, releasing different photons of light on the way. Alright, so go ahead and pause this little video at this moment here and just take a look at the different little emission spectrums for the alkali and alkaline earth metals. Okay, so that's atomic emission of light and emission spectrums in a nutshell. And understand that atoms can release energy in the form of light, and the different colors that you see are actually being associated with different amounts of energy, right? Your red light is going to be low energy photons of light, whereas your purple and violets are going to be your higher energy photons of light. So let's now take a look at a hydrogen atom and determine how much energy an electron is going to lose as it goes from a higher energy level like n equals 5 to a lower energy level like n equals 2. And so let's first figure out how we can determine the amount of energy that an electron in a hydrogen atom has at a specific energy level. So let's suppose we have our atom of hydrogen where here's the nucleus, here's the first energy level, or n equals 1, here is n equals 2, here's our third principal energy level right here, and here's our fourth principal energy level. And we can continue to draw these principal energy levels over and over and over and over and over again infinitely. However, we'll stop at the fourth energy level or principal energy level. And so let's suppose once again that this is our atom of hydrogen, and we have an electron that is in the third principal energy level. So we have an electron right here where n equals 3, and we want to know how much energy this electron right here has in the third principal energy level of our hydrogen atom. How can we determine this? Well, here's our formula right here that will allow us to determine the amount of energy that this electron here has in an atom of hydrogen if it's in the third principal energy level. E equals negative R times H times C, all divided by n squared, where E here is the amount of energy an electron in a hydrogen atom has at a specific principal energy level. R here is the Rydberg constant for hydrogen, and the Rydberg constant is different for each element. So the Rydberg constant for hydrogen here is equal to 1.097 times 10 to the 7th, and m to the negative 1 here is the unit. This just means that m here is in the denominator. If we take a look here, H is Planck's constant. We know that Planck's constant is 6.626 times 10 to the negative 34th joule seconds. We know that C here is the speed of light, which equals 3.0 times 10 to the 8th meters per second. And we have n squared here, where n is the principal energy level that the electron is in this case here, n equals 3. So we can determine the amount of energy this little electron here has in our atom of hydrogen if it's in the third principal energy level by using this formula that we see right here. So let's go ahead and apply this formula to a problem and see how it works. And so in this first example, it says to calculate the amount of energy that an electron in the sixth principal energy level of a hydrogen atom contains. So we have an electron here. If this represents a hydrogen atom, we have an electron that is in the sixth principal energy level. Here's n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and n equals 6. So our electron here is in the sixth principal energy level, and we want to know how much energy this electron here contains if it's in the sixth principal energy level. Well, how can we figure this out? We can use this formula right here. E equals the energy of this electron in the sixth principal energy level is going to equal negative R, which is the Rydberg constant for hydrogen, times Planck's constant, times the speed of light, all divided by n squared, where n is the principal energy level that this electron is in. So let's take a look here. We know that the Rydberg constant for hydrogen is this right here, 1.097 times 10 to the 7th, and meters here will be in the denominator. We're going to multiply this by Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds, We're going to multiply this by the speed of light, 3.0 times 10 to the 8th meters per second. And then we're going to go ahead and divide this all by the principal energy level that this electron is in. We know that n here equals 6, so we're going to take 6 here and we're going to square it. And so when we put all of this in our calculator, we're going to end up with negative 6.06 times 10 to the negative 20th. Let's see what units are left over. We have meters on the bottom. We have meters on top. They will cancel. We have seconds on the bottom and seconds on the top. And they will cancel, leaving us with joules. So how much energy does this electron in the third principal energy level of in the sixth principal energy level of our hydrogen atom contain? It contains negative 6.06 times 10 to the negative 20th joules. And you're wondering, well, how can we have negative energy? Well, the amount of energy that this electron has in the sixth principal energy level of a hydrogen atom is going to be negative, and for reasons that you will learn about in a physics class or in a higher or more advanced chemistry class, you will learn why this the energy of an electron is in fact negative. However, just for purposes of a beginning level high school chemistry course, understand that the energy right here that this electron has is going to end up being negative. So now that we know how to calculate the amount of energy that this electron has in a given or specific principal energy level, we are now going to learn how to figure out the amount of energy that this electron will release if it goes from the sixth principal energy level to the first principal energy level, for example. So let's learn how to calculate that next. So what if we want to calculate the amount of energy that an electron releases as it goes from a higher principal energy level to a lower principal energy level? Well, we can use this formula right here. The change in energy is going to equal negative R times H times C times 1 over n squared, where n squared is the principal energy level that that electron is going to end up, minus 1 over n squared initially. That is the principal energy level that that electron is in initially. And so here's our formula that will help us to determine the amount of energy that an electron is going to release as it goes from a higher principal energy level to a lower principal energy level. So let's go ahead and apply this formula to an example problem. Let's take a look. In this second example, it says to calculate the amount of energy released by an electron in a hydrogen atom going from n equals 5 to n equals 2. So we have an electron in a hydrogen atom. Let's suppose this is an atom of hydrogen. And it looks like initially the electron here is in the fifth principal energy level. So n here initially, the initial principal energy level that this is going to be in is 5. And what's going to happen is that this electron here is going to release some energy, and it's going to drop down into the second principal energy level as it does so. So this electron here is going to jump down into the second principal energy level, and as it does so, it's going to end up releasing some energy, right? It's going to end up releasing some energy, and that is what we're trying to figure out. We want to know how much energy this electron here is going to release as it goes from n equals 5 to n equals 2 here. So how can we figure that out? Well, we can use this formula right here. The change in energy is going to be equal to the negative Rydberg constant times Planck's constant times C, all divided by 1 divided by n squared of the, where n here is the final principal energy level that that electron is in, minus 1 over the n squared, where n squared here is the initial principal energy level that that electron is in. So here we go. Let's do this. To get the change in energy, to get delta E here, we are going to take negative R, which we know the Rydberg constant for hydrogen is 1.097 times 10 to the 7th meters to the negative 1 power. We know that Planck's constant is 6.626 times 10 to the negative 34th joule seconds. And we know the speed of light is equal to 3.0 times 10 to the 8th meters per second. And we're going to end up multiplying this all by 1 over the final principal energy level that this electron is going to end up with which is the second principal energy level, so 2 squared, minus 1 over the initial principal energy level that this electron was in, which was the fifth principal energy level, and we're going to square that. And so when we put this expression in our calculator, we're going to end up with a change in energy equaling negative 4.58 times 10 to the negative 19th. Let's take a look at what cancels out so we can figure out our unit here. We have meters in the denominator and we have meters in the numerator. They're going to cancel. We have seconds in the numerator and we have seconds in the denominator. They're going to cancel, leaving us with joules left over, right? Leaving us with joules left over. So the unit that we are going to put on our change in energy is going to be equal to this right here. And because the sign of our change in energy is negative, that means that energy is released. So going back to the original question, calculate the amount of energy released by an electron in a hydrogen atom going from n equals 5 to n equals 2. How much energy is going to be released as this electron goes from the fifth principal energy level to the second principal energy level? It's going to end up releasing 4.58 times 10 to the negative 19th joules. Let's take a look at one more example. This third example, it says to calculate the wavelength of light released when an electron in a hydrogen atom falls from n equals 3 to n equals 2 and determine its colors. So we have an atom of hydrogen. Once again, here is our atom of hydrogen. Here's the nucleus. Here's the first principal energy level, the second principal energy level, and the third principal energy level. And initially this electron here is in n equals 3. And the electron is going to fall into the second energy level, so the final principal energy level here is going to be equal to 2. We know that a certain amount of energy is going to be released as this electron goes from n equals 3 to n equals 2. And so what we can do is we can first figure out the amount of energy that's going to be released using this formula right here. So we're going to find the amount of energy, or the change in energy, first. Once we're done finding the change in energy, what we can then do is plug it into this formula right here. Here's our E value that we found in our first step, and we can solve for frequency. So in our second step, what we're going to do is we are going to use E equals H times nu, and we are going to solve for frequency. In our third step, what we can then do is plug the frequency value that we just figured out in step 2 into this formula right here. C equals lambda times nu, and we can end up solving for lambda, which is the wavelength of light that's released. We can then look at our data, or our table right here, and determine the color of light that is going to be released. So in our third step here, what we're going to do in our third step is we are going to use C equals lambda times nu, and we're going to end up solving for lambda. So let's first start with our first step. We need to find the change in energy using this formula right here. So to get the change in energy here, we are going to take negative Rydberg constant for hydrogen which is 1.097 times 10 to the 7th meters to the -1 power, times Planck's constant, 6.626 times 10 to the -34 joule seconds, times the speed of light, 3.0 times 10 to the 8th meters per second, times 1 divided by the final principal energy level that the electron is in, and we're going to square that. So we're going to take 2 squared, 1 over 2 squared, minus 1 divided by the initial principal energy level that the electron was in, and we're going to square that. So the initial principal energy level was our third principal energy level, and we're going to square that. And when we put this in our calculator, we're going to end up with -3.03 times 10 to the -19th joules. So this is going to be the change in energy as this electron here goes from the third principal energy level to the second principal energy level. Let's now determine in our second step here the frequency of the light that has been released as the electron goes from n equals 3 to n equals 2. And so we know that energy equals Planck's constant times the frequency. And if we want to figure out the frequency, we're going to divide both sides by Planck's constant. And so, to figure out the frequency, we simply take the energy and we divide it by Planck's constant. However, we can't have negative frequency, so what we're going to end up doing here is we're going to end up turning our delta E here into a positive value, which is 3.03 times 10 to the -19th joules. We are going to divide this by Planck's constant, which is 6.626 times 10 to the -34th joule seconds. And when we put this in our calculator, we're going to end up with a frequency of 4.57 times 10 to the times 10 to the 14th. Joules will cancel, leaving us with s to the -1 power, which is the same thing as hertz. And so now that we know our frequency, what we can do in our last step, in our very last step here, is we can plug the frequency value that we just figured out into this formula right here and solve for lambda. So we know that C equals lambda times nu. We're going to divide both sides by nu. Nu is going to cancel, and so to get the wavelength of light, or lambda, we're going to take the speed of light and divide it by our frequency that we just figured out. And so we know the speed of light is 3.0 times 10 to the 8th meters per second. We know the frequency of our light now, which is 4.57 times 10 to the 14th hertz, or s to the -1. And when we put this in our calculator, we will end up with 6.56 times 10 to the -7th. This will cancel with this, leaving us with meters. This is the same thing as 656 nanometers. So here is the wavelength of light that is going to be released, and if we take a look at 656 nanometers, we can see that that is going to be very close to this color of light right here. So we can say that it is reddish, right? We can say that it's not quite red, it's approaching orange. So we will say that the color of light here that is going to be released as this electron here falls from the third principal energy level to the second principal energy level will end up having a reddish color of light. So if you like what you see, go ahead and click that little bomb in the bottom right hand corner, and that will subscribe you to my channel. And feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.